Hi friends, today we discuss the Laplace transform. So Laplace transform is very useful to solving complicated differential equation or integral equation. So first we use the Laplace transform to transform those differential equation or integral equation to a more simpler differential equation, and we solve them, and then by inverse Laplace transform we again get back the original solution. So in this way Laplace transform is very useful in mathematics or in any other branches. So today we start with Laplace definition of Laplace transform and see some elementary functions and their Laplace transform. This course is very useful for undergraduate and postgraduate students in degree or in engineering. Let's start. So definition of Laplace transform. So suppose you are given a function ft, capital Ft, for t, where t is a positive parameter, then the Laplace transform of ft denoted by L of ft or Fs is defined. L of ft, Fs equal to 0 to infinity e to the power minus st into the given function ft. So Laplace transform of ft is 0 to infinity e to the power minus st ft, provided this limit exists. This limit should integral should be exist, because this is an improper integral. Here the upper limit is infinity, so this limit has to be exist. In that case we say that this is a Laplace transform, where s may be a complex or real parameter. Now see some Laplace transform of some elementary functions. Now start with the most simplest function 1. So what is L1? So L1 will be 0 to infinity e to the power minus h. This term is fixed always in the Laplace transform into this our function 1. Here 1 is the function, so into 1 dt. So this is 0 to infinity e to the power minus ht dt. Now we have to calculate this integral. So this is an improper integral. So we change this infinity to p and taking the limit p tends to infinity. This is the way we solve integral equation. So improper integrals. So 0 to p e to the power minus ht dt. Now integrate it. So this becomes e to the power minus ht by minus s, and limit will be 0 to p. So limit p tends to infinity e to the power minus ht by minus s, and limit 0 to p. So limit p tends to infinity, put the value of p, e to the power minus sp, and put, if you put 0, then you are getting in the, this value becomes a 1. So e to the power 0 is 1, anything to the power 0 is equal to 1. So e to the minus sp minus 1 by minus s. Now look, this function goes to 0. So this is goes to 0 at p tends to infinity. When your s is positive, s is a positive, if s is positive, then this tends to 0. So why this is happening? We see that e to the power minus sp can be written as e to the power sp, 1 by e to the power sp. If s is positive, then this goes to infinity. So if this goes to infinity, the whole thing goes to 0. But if s is negative, we can say, if s is negative, then this term becomes a positive, and in that case this goes to infinity. So in that case integral will be not convergent. So we need here s has to be positive. So since s is positive, we say this e to the power minus sp goes to 0, and 0 means this minus s minus cancel out, 1 by s is the answer. Next, LT, we found want to find the Laplace transform for t. So LT will be 0 to infinity e to the power minus st term fixed, and now multiply by t, because t is the given function. So again this is a improper integral. We write it like limit p tends to infinity and replace infinity by p, and t e to the power minus st dt. Now here we use integral by parts. So integral by parts, we suppose t is the first function and e to the power minus st is the second function. So in the first function, we first keep t as it is and integrate this e to the power minus st. So t e to the power minus st by s, and limit will be 0 to p, minus, we differentiate this t. So differentiation of t is 1. So here we have only 1. So we just did not write it as a, because it is as a multiple. And integration of this e to the power minus st. So integration of e to the power minus st gives you e to the power minus st by minus s. Now we keep it as it is. First function, this part is keep it as it is, and now we integrate this second part. So second part e to the minus st by minus s. So again this minus s comes down, so it becomes e to the minus st by s square. Now put the value of 0 and p. So we put the value 0 and p here. So first this t into e to the power minus st. If we put p here, p into e to the power minus sp by minus s minus 0. We put if t equal to 0 minus, now we put t equal to p e to the minus sp by s square minus 1 by s square. If we put 0 here, so this becomes a 1. So this is 1 by s square. Now we want to calculate the limit of this thing, p e to the power minus sp. Now p e to the power minus sp here, limit p tends to infinity. So this can be as p by e to the power sp. Again we have a condition that s has to be greater than 0. So this integral is true for only s greater than 0. So this, now use the L'Hopital rule. If we use the L'Hopital rule, we can differentiate this numerator and the denominator to differentiate. So with respect to p, so if we differentiate p with respect to p, then we get 1 here, and if we differentiate e to the power sp by p, then s e to the power sp. Again, this if p tends to infinity, this becomes an infinity, and 1 by infinity. So this limit tends to 0. So p tends to infinity, this becomes a 0. This is already 0. Similarly, we already previous example looked up, this becomes a 0. So only left is this minus 1 by s square, and here another minus is present here. So minus minus plus and gives a 1 by s square. Now another important elementary function, e to the power minus e to the power at. So Laplace transform e to the power at can be written as 0 to infinity e to the power minus st into e to the power at dt. Now we write this as a limit p tends to infinity 0 to p, and we just add this power. So if we add and take a minus outside, then we can write this is minus s minus at dt. Now simple integral, if we integrate it, so we get e to the minus s minus at by minus s minus a 0 to p, and put the value of p and 0. So we get e to the power minus s into p minus 1 by minus s minus p. Again, if we put p tends to infinity, this goes to 0. This is tends to 0. So we get minus cancel, this minus and minus cancel out. So 1 by s minus a. And here condition is s minus a has to s greater than 0, because we need this term is positive. This term has to be positive, greater than 0. Now the sine function, limit Laplace transform sine at equal to 0 to infinity e to the power minus st sine at dt. Now we use this formula. Sine of at can be written as e to the power iat minus e to the power minus iat by 2i using Euler's formula. So this is a basic Euler's formula. Using Euler's formula, we can derive this thing. So we just put this value instead of sine at and just multiply it. So if we multiply, then you get this this 1 by 2i is comes out 0 to infinity e to the minus s minus a by t, and e to the minus s plus ia by t. So using the previous formula, where we already derived that Laplace transform e to the power at is 1 by s minus a. So here we have s minus ia. So we just simply write 1 by s minus ia, and for this we write 1 by s plus ia. Now simple, if we add and calculate, so we get that a by a square plus a square. So this is the Laplace transform of sine at. Similarly, we can also obtain the Laplace transform cos at. So for that, we use this formula. This is the formula of cos at. Cos at equal to e to the power iat plus e to the power minus iat by 2. We just put the value, and using the previous theorem, a simple calculation, we obtain that Laplace transform of cos at is given by s square plus a square. So just remember that for sin at, we above here we have a here, and for cos at we have a s here. and the denominator is always same. Now take the hyperbolic function. Again we will use the similar tricks. We use the definition of hyperbolic function sine hyperbolic at is equal to e to the power at minus e to the power minus at by 2. We put these values and use the previous formula, and we can obtain. You can pause this video and take the all the detailed calculation. It is just simple putting the value and using those formulas. That this is equal to a by a square minus a square. And similarly for cos hyperbolic at, you can do similarly. And cos hyperbolic definition of cos hyperbolic at is e to the power at plus e to the power minus at by 2. This is the definition of a cos hyperbolic t. Again using the similar formula, we have cos hyperbolic at is equal to s by a square minus a square. Here remember that this s has to be greater than mod a, because for the first function here, for the first part, you need to, this term is positive, this term is positive, means s minus a has to be positive, that is s is greater than a. And for this part, s plus a has to be positive, so s plus a has to be positive, that is a is s is less than minus a. So in this way you have to find that s has to be greater than mod a. Next in the next lecture we will see some elementary properties of the Laplace transform.